Right, hello everybody. We're going to talk about service meshes. There are some predicates to service meshes in the first place. In this particular implementation, we are dealing with containers and Kubernetes. So if I could get a show of hands, who here is using Kubernetes in a production or test environment right now? Very nice. And how many people have kicked the tires on Istio in some way? Okay, and who would like me to define the term service mesh? Okie dokie, we're going to have fun. So this is a technical deep dive into Istio and network security implementations. We do go through the definitions. I will skip over some of the perhaps less interesting parts then for who we have here today. So hello, I'm Andy. I have done a little bit of everything from development and operations through security and architecture. I'm from a consultancy called Control Plane, which is continuous delivery practices for container and Kubernetes security, which is engineering broadly. I want to talk about service meshes, network threats, and enhancing security. And I'm going to make a bold claim that sounds a lot like this. Service meshes are the solution, I'm not sure if this is actually suitably, are the solution to network security. Because we can't trust anything. The internet was built with trust between everything, and unlike the origins of the internet, we're not just a bunch of academics running trusted workloads anymore. Critical systems and, of course, light bulbs and toasters are being put online rapidly, and traditional perimeter security and firewalling are provably not enough to keep systems secure. So, Istio, we can fix complexity with further abstractions and indirection. Istio won't solve distributed transactions, but it will solve other shared distributed system problems that we all have, including load balancing and fault tolerance, traffic routing and shaping, request tracing and observability, and end-to-end enhanced network policy and inter-service security. The network is unreliable and service meshes are here to help. But it's complex. It's solving hard problems, but if we don't understand the security features that are offered, we can't be sure we're using them correctly, and there are quite a number of features offered in this particular service mesh. We'll examine the old way, how this new secure transport is achieved, the mechanisms for bootstrapping trust, and the security and observability enhancements Istio promises. So, we used to have to use in-application libraries to get these distributed system fault tolerance, this functionality. So Netflix set the scene for this with microservices in general and commoditized distributed systems in particular with a slew of libraries over the last 10 years of cloud. Their suite of tooling is industry standard for JVM-based projects, but does not offer much cross-language compatibility. There are other things that we would need to stand up to match Istio's feature set here, the most heinous of which is internal public key infrastructure. And for zero downtime releases, we still need some sort of advanced DNS or root level service mechanism to match what Istio promises. So, Istio promises to centralize this complexity with a service mesh. There are two major components to a service mesh which are common to any network. They are the data plane, which we know as the network or the fabric or the copper or fiber, a control plane, which includes generally hardware routers or switches and their configuration, as well as things like software bridges or virtualized network cards, SDN routing infrastructure like your cloud provider's routing tables. And then finally, Istio's data plane is made up of Envoy, these sidecar proxies en masse next to every application. Every service on the mesh must have a dedicated Envoy proxy sidecar. Envoy is also used for ingress and egress gateways, and any proxy that conforms to Envoy's API can integrate with Istio, although to all intents and purposes, this currently just means Envoy. Envoy is a layer 4 to 7 proxy, similar to Nginx in some modes or HA proxy in general. And each Envoy instance is used specifically in proxy mode. and deployed as a sidecar for every application instance that is on the mesh. Separately, the control plane manages centralized configuration and injects that into each Envoy instance, so we have unified policy enacted individually by these Envoy actors. This is, of course, an idealized enforced governance situation. Some requests that require centralized information lookup, such as rate limiting, which is also offered and again implemented in the sidecar, also hit the mixer, which is the general purpose policy and telemetry hub down there in the middle. And this provides a uniform way to secure, connect, and monitor microservices, and provides security and identity primitives for workloads. I will explain what that means momentarily. Finally, we have zero trust networking. This essentially says, trust nothing, revalidate everything. It's underpinned by dynamic workload identity, which is provided by the SPIFFE project and used as the basis for the TLS certificates that are generated, given to each sidecar proxy, and used for mutual TLS authentication between services. This workload identity is distinct from user identity, which we would associate with things like OAuth, SAML, JOTS, and all those horrible things. So using SPIFFE, Istio provides automatic, free, end-to-end TLS for workloads. This doesn't protect you from a remote code execution in a front-end service, of course, but it does prevent that compromised service from talking to anything except what it is supposed to. This is referred to as limiting the blast radius, and is the central concept of secure systems design. Istio does not obviate intrusion detection or sensible network topology, but it does allow us to reason and secure the environment more accurately with a higher degree of fidelity. So, what does a network need to be considered a service mesh? Theoretically, with zero application code changes, that's not entirely true, because when running the request tracing, we have to instrument the HTTP headers of the request response, because everything here is implemented by the sidecar proxy. So it can't correlate the internal workings of your application. If two requests come in and the latter one is responded to more quickly than the first, there's no correlation between the inbound and outbound traffic. That's the one change that is required. So, unfortunately, Istio has taken a long time to become ready, and kind of looked like this for quite a long time. This is still very much a case of buyer beware. There is a huge amount of complexity hidden beneath. It's difficult to debug from a network perspective, but for an organization that has high compliance requirements, or for example, mutual TLS as a security checkbox, the advantages that it brings over spinning up your own infrastructure are, I think, clear. So how does this work? Using the service mesh construct, a dedicated network, which is the only way for services to communicate. In old school networks, a node was connected to its neighbors. Then we moved to hub and spoke star topology. And a mesh is a network with multiple routes between individual nodes. This may sound simple, but when spanning network segments or whole networks, it becomes more complicated. And the extreme example, a fully connected network, is the sort of service mesh that we are talking about and that we want. Every node is able to talk directly to every other node. So, in Istio's case, every node has a persistent TCP connection to every other node. This is the mesh. Entry to the mesh is granted to each application via a proxy. There is one proxy per instance of a service. Of course, we're using Envoy here, and it is Envoy that is making these connections to other envoys on behalf of the applications behind it. The mesh still transits over Kubernetes container networking interface network, but it's re-encrypted. So the mesh is a set of encrypted TCP connections between dedicated proxy servers, in Envoy's case, using HTTP2. Istio is just a load of Envoy sidecars. It's really that simple. If you look at the other service mesh offerings that are launching at the moment, AWS App Mesh, just Envoy with a different control plane. Envoy has been shipped in 3 or 4 products right now. It is rapidly becoming, or sort of eating the lunch that maybe Nginx could have protected or guarded. So, one more thing to note. The sidecar pattern means that once we're in a Kubernetes pod, we're in a shared network namespace. That means access to the loopback adapter is shared between every container running in that pod. When we place a sidecar into the same network namespace, they're in the same pod, they're in the same network namespace, and thus they're in the same trust boundary. So we implicitly trust the Envoy proxy to act on behalf, not only of the application, but also it is within the same security boundary. Envoy is just using IP tables to redirect all the traffic in and out of that network namespace to itself so it can make policy decisions and send the traffic onwards over the mesh. One more time, all services are isolated from each other and from the mesh with the only route of ingress or egress for those services through the sidecar proxy. The proxy intercepts all traffic and routes between instances with various high availability routing algorithms. And yes, here we are, just further meshing. Mutual TLS is used as not only an encryption and security layer, but also for something called secure naming, which says if we trust the certificate authority that has signed the certificate, then we can also trust the contents of the certificate signing request, which include the common name. Therefore, we're able to apply RBAC roles and make routing decisions based upon the contents of the TLS certificate. From this simplistic diagram of just the data plane to the whole system, back we go. So Istio gives us some free security, but how? We'll briefly trace a request through this system and have a look at the encrypted data flow between applications that Istio is stewarding. This is the mesh flattened to show the path of a packet. Stage 1, we have ingress from the internet or from another network. Stage 2, TLS is terminated on the ingress proxy. Mesh mTLS is then spoken between the ingress proxy and point 3, the sidecar for service A. This TLS identity is provided by Citadel, which is Istio's certificate authority. Stage 3, Envoy terminates the mutual TLS of the internal communication. So that's a different certificate from the one that the website is advertising on the load balancer. And at this point, at stage 3, the proxy extracts the service's identity. This is the common name from the TLS certificate, and applies RBAC rules. It inspects the plain text headers because all the applications are just speaking HTTP to the sidecar, which then bundles that up in a TLS session, and an HTTP2 persistent socket is already open. So that means that the Envoy sidecar proxy is able to make layer 7 routing decisions, including load balancing based on not only the path and applying RBAC to those things, but also arbitrary matches for cookies or whatever information you wish to tag your requests with. Policy decisions are also taken at stage 3. If the ingress proxy is permitted to talk to service A, then Envoy will allow that communication. At that point, we then have essentially a delegated request here. So the user has made a request at 1, it's hit service A at 3, but service A actually needs to speak to service B to gather some more information about the request. So at point 4, a plain HTTP request on the way out of service A is then rebundled back onto the mesh TLS, and the same process as between the ingress proxy and service A occurs between service A and service B. Unbundling, secure name checks, policy decisions. Again, in this case, it appears that service B needs to make a request to something out of the mesh entirely. So then it rebundles the request, passes it over this re-encrypted mTLS session to the egress proxy, which then makes an outbound request to something outside the mesh, say perhaps a hosted MongoDB instance or something like that. And then, of course, the packet comes all the way back, and we end up reversing this whole chain as we go back and communicate with the end user. So, of course, these, yes, yeah, there we are. So, this is the same diagram, but from a different perspective, with a focus on the services in the mesh. No user service can access the mesh directly. We have this main service to Istio proxy, flight service to Istio proxy. That is the only way they can communicate. And the centralized configuration is enforced by Envoy as a result of the Istio pilot control plane application pushing that configuration data into each of those Envoy instances. It should be noted that that configuration data push does not require a restart of the Envoy service. It has full API-driven configuration and operates an immutable state, an immutable configuration model. So a connection will use a model until the API configuration, the configuration is updated via the API, at which point new threads point to the new version of the configuration, but they both sit in memory until the network connection is drained, which means we're able to run multiple different configurations in the same Envoy sort of in perpetuity. And that, again, is part of the magic of this system. Instead of hanging up to do a soft reload of configuration, Envoy will just happily carry on with as many different types of configuration as you can throw at it. So let's have a look at the security model. We've got a lot of potential attack vectors for a modern web application: insiders, hijacked services, microservices attack surface. Audit and compliance are brittle, fine-grained models. And courtesy of Louis Ryan, Istio's tech lead, this is the threat model that we are looking at for Istio. This is what Istio deploys. As you can see, there are a large number of services. It is not the simplest tool. First of all, we have a configuration writer for Envoy's API and pilot. Mixer is the central metadata and policy store. Citadel is the CI component. Galley is configuration component. The Sidecar injector places that Sidecar container in every pod. So that dynamically and transparently adds a service to the mesh. We have Proxy, which is Envoy, Proxy Init, which is the IP tables rules. Grafana, Jaeger, and Prometheus are the observability and tracing tools. And finally, a StatSD exporter bridge. That's what I just said. Why is this important? Well, this is what I think of when I think about images pulled straight from the Docker Hub. So Istio gives us an opportunity to treat all our workloads as hostile and apply a more granular network policy. And we do that with Envoy. You can see there the shared network namespace. Envoy sits next to every service in that service's own network namespace, as with any pod. It intercepts all requests and applies Istio's policy and provides network transparency, so the service is not aware that it's being proxied. A loopback bypass for local proxy-aware apps to access a layer 7 service via localhost instead of the virtual IP provided by the Kubernetes service construct. And some security. So it avoids granting unnecessary privileges to proxy processes. If we annotate a namespace in this manner with Istio injection, then the Sidecar injector will add Envoy, and you sort of magically just have what would otherwise be a resource YAML with the addition of an init container and Envoy itself. So this is what a pod looks like when Istio has been injected. You see that we have we've got the demo application, book info, and then these other images just appear as with any other Kubernetes resource. Of note is that those two proxy containers are both really heavyweights. The init container configures the namespace and requires the kernel capability capnet admin. Although it shuts down after the configuration is loaded, it should be noted that this is a highly privileged capability and can cause mischief if misused. There is actually work underway to move the whole of Istio to a CNI plugin, which will make debuggability even more difficult, but it will remove this this init container construct. So let's just have a look at the init container while we're here. I'm very happy to note to you all that the world is run on bash, and the networks that glue the bash together are marshaled with IP tables, and Istio is no exception. I present to you Istio IP tables.sh, the init script responsible for setting up port forwarding for Envoy. There's evidence here, essentially. You can see we've got various exclusions. So I said that the IP tables rules take all traffic and direct it to Envoy. We can set bypasses for that if we so desire. And there we are. That is the Istio magic, just performing the redirection from all networks to Envoy, and then Envoy is able to make those routing decisions and actually make outbound requests from within that network namespace. There are some hidden gems. SSH is not handled by Envoy. I mean, what's SSH doing in the container anyway, as we all know? And there's a local host exclusion and IP white and blacklisting. Finally, drop IPv6 if configured to do so. Otherwise, IPv6 can do what it likes. So very much like with whatever VPN you're running, if you have an IP6 enabled TCP IP stack, you're probably leaking stuff everywhere. We should disable IPv6 unless it's well configured on our devices. The same goes for our production applications. So that's the init of the container. Let's have a look at what Envoy does. The sidecar is injected automatically if we see the annotation we had earlier. And here we can query the status of the mesh. You actually see up here we've got what looks like Istio control, but due to the huge discourse generated around the pronunciation of cube control, I would like to propose that this is actually Ioctal. I'll leave that to you for your own judgment. So here you can see there are 4 different Envoy synchronization mechanisms. We're not dealing with simple systems here. There is a lot of complexity that Istio masks, and Envoy is a serious part of that. So we can retrieve information about cluster configuration for the Envoy instance in the specified pod, which is all very nice. We can see the mesh between the services here. This is the layer 4 stuff, IP and port based. But what about the layer 7 TLS security? Or arguably layer 5? I'm willing to have that discussion afterwards. So a reminder about the mesh. It is an encrypted, always open HTTP2 network which connects each proxy to every other. Traffic over the mesh is then encrypted again with this mutual TLS and encapsulated, ensuring the cryptographic identity of the calling service is known and not only possibly spoofed in an HTTP header. A brief refresher on public key cryptography. It is a way to send a message that only the intended recipient can read. We can have a public key that allows somebody to open the mailbox and put their message to us in. There is the message. But a different key is required to unlock the message. There is no reverse engineering. You can't use the public key to decrypt something that's been encrypted with the public key. Only the intended recipient can use this. This is the fundament of TLS. This is Diffie-Hellman. So, for example, on the internet, self-signed certificates are bad. We don't trust them. They may be the sign of a man-in-the-middle attack. Now, what we do in Istio is actually have a self-signed certificate authority, and we keep the private keys for that within the cluster. Is this better or worse? Well, arguably better, because if somebody has compromised the cluster, then the leaking of your private keys, which have to be in there anyway because of the certificate authority minting new certificates for all new services every hour, and they're rotated on the hour, then you're probably having a worse day if someone can get to those because they can probably read the state store, probably read all the secrets, etc. So I would argue that running, and in fact, Kubernetes does this itself when it bootstraps its own control plane. And it has 7 different certificate authorities for segregation of duty. And so Istio is doing the same with a self-signed certificate. It also uses mutual TLS. So whereas normally we would just have this one-way TLS, with mutual TLS, we are doing TLS Handshake twice. This means that we're verifying the identity of the server like we do on the public internet, but the server is then reciprocally saying, okay, well, prove who you are as well, and I will see if I trust your signing authority, and then if I do, trust the certificate signing request data, like the common name or perhaps some extended attributes. What I've just described is the essence of the secure naming service in SPIFFE. We're going to introduce another new concept here. In Istio, SPIFFE is the new concept, and you can see here the subject alternative name of the certificate is a new form of URL. SPIFFE is secure production infrastructure for everybody, and it is a way of assigning an identity to a dynamic workload. What that means is if I spin up a deployment with 20 pods, each one of those pods can have its own identity. Why is this useful? Well, in the event of a breach, for example, you can know that the logs coming out of those pods were cryptographically signed up to a certain point. It means that you can lock down that singular service at multiple levels. So, of course, you can address it as a pod, but with identity, suddenly we have an extension of the guarantees that are provided to us. And, of course, this is cryptographically backed identity, so as long as we trust that the mathematics that TLS is based on for the ciphers in 1.3 is not vulnerable or broken, then we can build out our trust in the system. And yes, sorry, next slide. So how does this work with Citadel? So this is what the Citadel image itself looks like. If you take the Docker file and just explore what's in there, it's a from-scratch image, which is the best of practices, because if I get a remote code execution into this container, what can I do? I can't run bash. I have no other language interpreter. All I have is a statically linked Istio CA binary that I would then have to do some sort of bytecode or like return-oriented attack on, which is ridiculously difficult and really raises the bar. So scratch images are the best, and we should always ideally use them. And we can see a couple of other things. We've got the CA certificates, which is the certificate chain for the global public key infrastructure, the trust stores that our TLS certificates for website navigation are based on, and the contents of the upper overlay are sort of generic files that go into all Docker containers. Let's see if it's running as root. Yes, unfortunately, if we use sysdig to trace a running invocation of this container, it is running as root. We're not using user namespaces in Docker or Kubernetes, and as a result, this process is actually running as root on the host, because, of course, containers are just a window to the world through which a process looks. Now, we have multiple other layers of security here. We use seccomp. We are using namespaces as a security mechanism, but as best practice, we would ideally not be running that as root. So what does Citadel actually do? It implements a subset of the whole SPIFFE specification, which has a concrete implementation in a tool called Spire, which is a topic for a different talk. But right now, all SPIFFE is doing is enumerating the service accounts that are mounted into deployments. Is this a good thing? Arguably not, because when I'm talking about this granularity of workload identity based on a per pod basis, well, all we're doing here is enumerating the service accounts, generating certificates for them, and then mounting the certificate into the Envoy instance next to that pod. If we have a very granular decomposition of our security models such that we are using a separate service account for each concern, then we will just be sharing at the deployment level, which is probably also the service level if you have a one-to-one mapping of services and deployments. So this works right now. There is a phase 2 coming for this, but I'll run through what it looks like right now. So we enumerate, well, first of all, we actually pull the private key for Citadel. We enumerate all the service accounts, and then we generate certificates with each of these SPIFFE IDs in. This is for a hypothetical deployment. And then you can see that it actually issues those certs finally, and it just sits in a watch. So if ever a new deployment is added and it has a new key, a new service account, Istio will generate that certificate. It also goes through and rotates these certificates every hour. There is not enough computational power on the earth, theoretically, to brute force one of these certificates in an hour. It's the trust upon which we base the internet, and of course you know that those keys on the internet last for generally a year, sometimes 3 or 4. So, back to the secure naming. This is the SAN and the TLS certificate, as we've mentioned, and we can add further information to uniquely identify these services. Let's just go and have a look at what SPIFFE is actually doing. As I said, SPIFFE is the spec. There's an implementation called Spire, which is slightly different. Again, the SPIFFE ID has a trust domain and a workload identifier, which in the case of Kubernetes, we use the trust domain, namespace, my namespace, service account, because that is the level of granularity that we are offered. There is work going on to fix all this. Kubernetes does not easily identify does not easily expose the identity of the pod downwards without various things like the downwards API. So what we're doing here is attesting, and attestation is the basis of SPIFFE ID assignment. We're attesting that we trust whoever identifies themselves as this service account is that person. Therefore, we can base our RBAC rules off them. We can allow them to enter the mesh because the cryptographic identity in that certificate is trusted by all the envoys because they share the public key of the signing authority. And as such, we've bootstrapped trust. It's all just, so SPIFFE actually generates an X.509 SVID, SPIFFE Verifiable ID document. There will be JOT extensions for this as well. It is the most common thing on their common request. And what that means is we're then able to generate an X.509 certificate with these extensions. So SPIFFE is just a standard for how an application can programmatically retrieve an identity from a trust domain and the short-lived credentials that go with that in order to put that identity onto a secure network. So using this API, libraries and tools can retrieve credentials that identify them automatically without needing any secrets code deployed, an inversion of control and based on these layers of trust. Istio does not work in this way, but it will soon. We're looking at having a node agent on each node running as root, and the magic of this is we're saying we trust the node anyway. If the node is compromised, then, if root access is given to the node is compromised. So let's also say that we trust a process running as root and have that pull back the metadata from process, use that in the CSR, and send that to the certificate authority, again, to bootstrap our trust. This is obviously slightly better than generically issuing certificates based on service counts, but comes with a huge amount more complexity. This is in the works. We are just using a chain of trust here, CAs, intermediates, and leafs, exactly like we do on the internet. And it's worth mentioning that SPIFFE is not the certificate itself, and it is not an authorization mechanism. These things are layered on top of the usage of SPIFFE and certificates, but they are, by definition, not what SPIFFE does itself. So back to the diagram, we have Citadel, the certificate authority, which requests the secure SPIFFE name, generates a certificate, pushes that certificate into Envoy, and Envoy now uses that in the request path for any traffic to and from the back-end server. We can retrieve information about the Envoy sidecar for a specific pod. It just has an HTTP API on 15,000 there. Here we see the cert chain is Envoy certificate that needs to be presented on the other side. The key is the private key paired with Envoy's certificate in the certificate chain. The root certificate is the root key to verify the peer's certificate. So in this example, we only have one Citadel in a cluster, so all Envoys have the same root certificate. However, multi-trust domain spanning is again being worked on, and the sort of thing that will make this, I would suggest, invaluable to an organization that requires that level of security. So, secure by default is a wonderful aspiration, often very difficult to realize. Sniffing network traffic is easy. Access to a node over which the data transits guarantees access to it. And without encryption, the traffic can be intercepted and logged. This is what the GCHQ and NSA have been doing for the last 20 years plus. Adding encryption to network communication hardens our services against interference, tampering, or eavesdropping, but is not easy to do. As we know, the service account, this separation of privilege is based upon least privilege at all stages. So, staying secure by default is not easy. Multiple layers of controls are required, and layering Istio RBAC on top of existing Kubernetes network policy provides some degree of this protection at layers 4 and 5. Whizzing through the last few slides, which are basically blocks of YAML for your later perusal. This is a higher fidelity network policy denied by default for Istio RBAC. You can see because the API version points to Istio. Here we're creating a service role, allowing service communication within a namespace. Here we're doing the same thing, but applying it per service. And everything that we have declared declaratively via Istio has been validated by the Galley component. Pilot has looked up the Envoy services that require the configuration, injected it into Envoy via the API. So all new requests get the new configuration, while old requests are left to complete safely with without configuration contention. Istio authorization is really strongly recommended. It is a higher level than network policy, than application authorization. But if you really, truly, madly require the capability to roll your own, Istio allows extensible integrations to plug into the mixer, which will let you shoot yourself in the foot at your leisure. So we also have, this is super exciting, and again, a kind of insane thing to imagine that would be in an open source project. You can enable authenticating the end user. This is called delegated end user authentication. So what this means is at ingress point to your mesh, you identify the user, you validate their JOT against the public keys provided against the signer, and you then exchange that for a token. And you exchange that token at every hop of the request through your infrastructure. This means that instead of having to run our own JOTs, and for example, JOTs are vulnerable to replay attacks, so the best practice is then to rotate them every time, which means we need a high availability infrastructure to issue and rotate those JOTs in our somewhere running highly availably. The sort of Kubernetes consolidation dream, and Istio by extension, says run everything in Kubernetes, because ultimately the thing will either be up or down, and your single point of failure then moves to the cluster, because you can run all these things highly availably in it. So this inter-microservice request delegation is really powerful. Again, it's under development. It's probably, I would say, safely 12 months before it's realistic to use or to think about using in production. And this phase is to support 2 or more hops for a single request. The security token service is what I was alluding to before. This is the authentication proof token I was describing. Almost running out of time, so we'll just keep on going through here. We also have traffic management applicable at the ingress. You see, it's the same flow, these ingress and egress proxies. We can apply rate limiting. We have all this configuration, which we can apply as code for security as code, compliance as code. And we can also re-implement that previous configuration by instructing Istio directly instead of the more generic rule there. We have telemetry built in. Obviously not a security feature, but useful for debugging and development. And we get free metrics, again, essential to any post-mortem or breach analysis. So what's next for the project? A huge laundry list of things. It really is large and complex, but in terms of preventing replication of the same functionality amongst multiple teams, multiple companies, it will eventually, I believe, be the ultimate consolidation of all this complexity. Thank you very much.
Well, thank you, Andrew. So we've got a few minutes now for questions. We've got 2 roving mics. So if you have a question, could you stick your hand up, and then we'll bring the microphone to you so that everyone can hear the question. Are there any questions?
Sorry, this is more of an Envoy question. It'd be quite a powerful, confused deputy. Is it a huge piece of code?
Envoy, so there is a foundation similar to the Apache Foundation called the CNCF, Cloud Native Computing Foundation, and Envoy is a graduated project of that foundation. The reason I mention this is because they paid for a security audit. So it's a modern C++ code base, excuse me. It came out with some glowing recommendations and some others were remediated. It's all public. It is a likely escalation point or a point of complexity, I agree. But by all accounts, it is well reviewed in its current state. Also, a common question everybody asks is, what is the performance penalty of running Envoy and Istio like this? It's a very difficult question to answer. Of course, one should always have benchmarks for their system and telemetry in place to identify the before and after. Istio can be adopted piecemeal, which means that you can just enable the bits that you want and perform your benchmarking. The official line is that HTTP2 encapsulation of HTTP1 traffic means you don't have to renegotiate the socket all the time. You have a persistent connection. So theoretically, the few milliseconds put in line by this Envoy proxying are mitigated by network retry code, but your mileage may vary. Hi.
Hi. Which parts of Istio are kind of easy to get going with? The auth stuff sounds quite complicated, but like, is metrics and tracing easier to get on with?
Yeah, I mean, so the official Helm chart allows you to turn basically the whole thing off and flick on whatever permutations you desire. The nicest, simplest thing to do is just enable the tracing and the metrics collection, because that all happens without intervention, essentially. I mean, the tracing does require annotation of, it does require instrumentation of existing code, but the metrics collection, which is things like your request throughput, your traffic distribution to various services, is really nice and free and easy. So yeah, that would be the first step. Obviously, my personal love is the mutual TLS stuff, which again is not particularly complex. The failure conditions in Istio are more like erroneous 503s that are more generally in Envoy. And if you look through the history of, there's a project called Fortio, which is their load testing project. There's numerous talks. KubeCon has a slew of these talks every year with regards to how the development process is maturing. So yeah, the complexity tends to come in understanding what Envoy is doing and how to debug it, whereas the other stuff is kind of lower level, less difficult bugs, I would say. Hello.
Hello there. Thank you. This sidecar pattern that you mentioned, has it had any sort of implication when it comes to chaos engineering? Does it make things simpler? Can you swap it out for?
So I mean, I didn't cover this, but there are fault injection patterns in Istio as well. So one can introduce network latency and jitter and change the request responses as an Istio primitive, which is just instrumenting the relevant code in instrumenting. It's just utilizing the relevant code in Envoy. So certainly, it's kind of it's a way towards chaos engineering. It's maybe not as destructive as a monkey would be in just pulling things, but yeah, you can go. I suppose you can even emulate that by setting your request latency to be 2 minutes or something, and then you're going to lose all the TCP connections, various other things. So yeah, there is some built-in stuff. I haven't really played with it, to be honest. I'm focused more on the uptime rather than further downtime. But yeah, that has been a consideration.
Thank you.
I think you said that it doesn't really identify users at the moment. With the user identification stuff that's being worked on at the moment, is that likely to be pluggable? I mean, how would you interface that with how you're currently managing access for users?
Yes, so it does integrate a little bit of end user identity stuff at the moment. What the next phase of that is, from my understanding, is basically the same pattern as they've introduced for the mixer, which is even internal implementations are utilizing the API. So they've already built the abstraction and they consume that internally. My belief is that that's what will happen. So you'd be able to use your AD or LDAP or SAML or whatever that is at the edge, because that is just a concern of the Ingress service, after which the token exchange service kicks in for the rest of everything else.
So you're saying you just need to get to the point where you can identify the user, and then you can convert that into a JOT which Istio
Yeah.
can understand, and it's just you translate. So anything the other side is down to you, somewhat.
Yes, so you have a request mapping between your, say, external and internal claims, if you like, or whatever you've configured on the Istio side. And then the veracity of those claims are verified by the fact that you've got that one-time token that you can exchange each request. So it's conceptually, it's not too complicated, he says, but in reality, I'm glad that I'm not designing it. Yeah, so that's what it will. That's currently the design document. Yes.